Okay, we are recording now. So good afternoon, everyone. Um, my name is
Good afternoon, sir.
my name is Kaycee Ezebialu. I am presently a graduate research trainee with Chevron Nigeria. I I have a BSc in geology, and then I have a master's degree in petroleum geosciences. And basically, this presentation this afternoon is going to be talking about basic principles of geomodeling, and I will be talking about it generally on the case study of my MSc project, which, by the grace of God, was done in Slumbeje, Nigeria. And for purpose of references, if you look at the people listed, their names are listed here. You see that these were really my classmates, the people, my project teammates. So I highlighted my name because I'm the person doing this presentation. So each of us have really worked as one thing or the other in that team, functioned as one thing or the other in that team. But believe me, there was really a lot of synergy in terms of team bonding and all that. So it was really a teamwork, everybody doing everything, but we still now have domain expertise from different members of the group. So the project is field development planning based on static and dynamic modeling of X field Niger Delta. So for purposes of outline, we'll look at the review, basically look at what literature has said about what we want to do, and then we looked at also the objectives, data inventories, and the softwares used to analyze those data, and then basically look in terms of workflow, what and what should you do, and when should you do what, and then challenges, recommendations, and conclusion. So generally, everything in the subsurface, you think in terms of teamwork, and like I explained on my first slide, talking about how we had the geologists, we had the petrophysicists, the geophysicists, and the reservoir engineer coming together to talk to themselves to generate a subsurface model. So here in the oil industry and the business of exploration and field development plan generally, teamwork is key. So together everyone achieves more. So in terms of literature, this field, the X field, is located in the coastal swamp depot belt of the Niger Delta onshore, and a couple of wells have been drilled. Generally, it's a completely underdeveloped field. So in terms of structures, you expect it to have brute force, rollover anticlines, normal force basically because you know you're dealing with the Niger Delta, which is passed as a sectional margin, and you begin to expect normal force because you know what you have there, what you expect to see. Just to highlight a little, in terms of interpretation and everything you do, as a geologist, as a technically sound person, you know where you are. You know what to expect. So your interpretation basically is using the information you already have about that field, your background knowledge about what you're doing, to now take informed decisions that will add value to your company. So the basic formations would be the Akata, the Abada, and the Beneath formations. So the project objectives included applying a defined reservoir modeling workflow for static and dynamic modeling, and then also the estimation of in-place hydrocarbons in the reservoirs found in the field, and then recommend the best case scenario in terms of least number of wells for good cumulative oil production. So the data that were available were basically seismic. Remember, just to mention again, it's very rare for you to see, for you to have every data you require. So the data you have, you try to make a sense out of. You try to use the things you have to try to take decisions. So in terms of data availability, we had seismic 3D volume. We had well data from 4 wells that already were drilled in the field. And then we also had reservoir fluid properties like your gas oil ratio, API gravity, water salinity. And then, like I said before, this project was done in Schlumberger, Nigeria. And so all the softwares we used were Schlumberger's proprietary, Petrel for basic seismic interpretation and static modeling, and then TechLog for petrophysical evaluation, and then Eclipse for dynamic simulation for the reservoir engineering. So the table below is kind of an inventory of all the data that were available for each of the forwards, and each of the forwards were named well A to D. So in terms of general workflow, what we did and how did we come about it? So we basically started from data QC and loading data, QC the data, and again, petrophysical evaluation down to geological interpretation, and eventually got to production forecast. So trying to kickstart what we are doing, basically what you see in the dark image is basically your seismic inline and cross line, and then the four wells drilled already drilled in as loaded in Petrel, and then you find below it the well log data as loaded as loaded in TechLog, and then by the right you have the trying to QC quality check the data to know what and what is what. So these you guys can see my mouse, can see my pointer moving. Can you?
Yes, sir.
So this
Yes,
log,
sir.
thank you so much. So this log basically would be what is called the bad hole flag. This is a caliper log. And so what this would try to do was to understand where the hole is bad, where we have where you have cavings and where you have swelling of information swelling up. And so you down because generally remember your caliper log is giving you information about the rugosity of the hole. So again, we saw that to be a problem, to mean that our caliper log is not of good quality. And again, we went further to notice that sonic log actually mimics resistivity log. And by way of digging further to really understand what happened, we found out that this sonic log was generated from resistivity log through what they call forced approximation. So going further, petrophysical evaluation was to be carried out. Sorry. And in petrophysical evaluation, basically what are you doing? You're just trying to understudy and characterize rock and fluid properties. So those will include your lithology, porosity, and saturation. So generally, if you look at this chart here, you see you find the rock, you see a reservoir, a non-reservoir, that's lithology. Then when you find a reservoir, is it hydrocarbon bearing or water bearing? When you have the hydrocarbon bearing rock, then you begin to ask yourself, do fluid evaluation to understand, is it gas or oil bearing? For each of them, you evaluate. And in evaluating, like I told you before, locate reservoirs, detect hydrocarbons, distinguish between oil and gas, and then go ahead to evaluate your saturation, porosity, permeability, and all the rest. So that's about that. And so the project proper, we were able to generate from our gamma ray resistivity and neutron density logs that we already had as data initially. We use these logs to actually make meaning out of the data in terms of petrophysics. So we're able to from this generate the volume of shale. We're also able to generate water saturation. And we understand the relationship between water saturation and hydrocarbon saturation because one is equal to water saturation plus hydrocarbon saturation. So having gotten the water saturation gave us an insight as to what the hydrocarbon saturation will be. And then again, we also computed for porosity and then permeability. Below here, you see the two reservoirs mapped in this field. You see them, their volume of shells, their net. Just analyzing them, you see that you're fine. You see that reservoir 2 and 3 is giving you, all of them, not just reservoir 2 and 3, is giving you a very low volume of shell in the range of zero point 0.0 something. So, and again, net to gross, which is your sand package over your total thickness, is also giving us something good, telling us that we have majority of the thickness to be sand. And again, porosity, as far as Niger Delta is concerned, 25 to 30%, which is excellent, which is also fine. And then our water saturation generally below 0.5. So telling us that we have good hydrocarbon saturation. And remember the relationship I talked about before now in terms of water saturation and hydrocarbon saturation. So we're able to also generate the contact, the contact. And if you look at the three reservoirs, it will be obvious that reservoir 1 and reservoir 3 are basically gas reservoirs. So with the presence of gas water contact, while reservoir 2 has both a gas cap and an oil ring. So that is evident in the presence of GOC and OWC. So in terms of geological interpretation, we went further to do a field-wide correlation across the 4 wells, drawing a cross-section from east to west. So we're able to look at the logs and then interpret across board. So that interpretation gave rise to fasci interpretations in terms of the environment of deposition. So we're able to actually map out our upper shore face sand. We're also able to map out the lower shore face petroleum and pro delta shells. ATG is raising his hand. Please unmute yourself and say something.
Okay, please, can you please state the softwares that was used to generate any of the models you're showing us as you're going?
Yeah, I have. Okay, thank you so much. Basically, basically, this was done on Techlog. When I showed you this, I mentioned that Petrel was used for seismic interpretation and model static model building, and Techlog was used to petrophysical evaluation, while Eclipse was used for dynamic simulation by the civil reservoir engineer. So, but I'll try to also look at it in terms of what you just mentioned. Thank you. So, for the petrophysical evaluation, everything we did here was on Techlog, which, like I said before, is proprietary to Schlumberger. Here, what we use here is Petrel for the geological interpretation, where we're able to distinguish three different fascias in terms of environment of deposition: upper shore face sand, lower shore face petroleum, and pro delta sand. And if you look at it, you see that by our knowledge as geologists, you see that porosity and permeability should be better in upper shore face sand and all that. So it tells us that we are really in the right place. We are really, all these things is using our data to eventually take a decision. If you see from where we started, from where I started this presentation, you see how we've been building on the knowledge that we're able to get from our data. So eventually, we also trying to do seismic interpretation, just basically trying to do a well to seismic tie to understand where you basically use that deterministic wavelet and then 4 anchor points. And because of if you understand what is called what's it called now? Surge and anti-surge. I can't remember. Surge and anti-surge data format. You understand what I'm talking about here. Our tops corresponded to the peak, while our base corresponded to the top. So we're able to basically generate a synthetic to use to match our wells to seismic before we went into seismic interpretation, fault and horizon interpretation proper. So these basically will be the horizons map. You can see this is the first horizon, this is the second horizon, and this is the third horizon. Each of them representing the three reservoirs, reservoir 1, 2, and 3 that I had mentioned earlier. Also, you see your faults, you see a general group of which is kind of a boundary fault, basically. Then you see the other synthetic and non-synthetic faults that characterize the Niger Delta normally. And so this will now be your false stick. The false they picked out, this will be the sticks that you generated from it. And so this tells you that what we are thinking about, that there are possibilities. But if you look, you see, just looking at your data, you see that you're already having closures, you're already having possible stuff. So you continue to query your data, you continue to do your interpretation to understand stuff. So basically, because our what we are dealing with is time, so we needed to convert to depth. So these will be the top maps of the trade reservoirs in time, and eventually it was converted to depth, and that depth map will be this, just to quality check quality check to make sure that what it is what it should is what it should be. You see the consistency when you compare the time map and the depth map. You see how they are consistent across the. So eventually, the velocity model was used to convert the surfaces from time to depth, and then generated depth maps for each of the reservoir bases. So sorry. So basically, that's what it is. And then the four sticks that we had picked, because of the fact that we have a zone we are interested in, the top of our first reservoir and the base of of the third reservoir. So we kind of slice it out to constrain our interpretation, both default and the both default, sorry, to constrain our false interpretation only on that area of interest. And that's why you're seeing the false cut from top and bottom. And this will now be those are four pillars that we use for sorry, that we use for modeling. And this will be default when it's already modeled, and then the horizons when it's already modeled. And then basically we looked in terms of gridding because remember, having modeled your fault and horizons, you need to grid it. Imagine the reservoir to be a big room, and if it's a big room, you know that geology, the earth is not homogeneous. So you now need to grid it in cells, in layers, or in cubes that represent each flow unit kind of, so that you can begin to talk in terms of homogeneous properties across those different zones. And having done that, we went further to now populate. Remember, we had gotten our petrophysical parameters, we had gotten our Fashi parameters. So we now, what static modeling is basically doing, trying to do, is to now populate those petrophysical parameters and Fashi parameters into these our um, our 3D grid that we've built. So to do that, we need to upscale our logs. Why do we need to upscale our logs? Logs, you're going to, every other thing you got here, both your horizon and your fault, are products of your seismic. And that those the seismic and the log, they don't have the same resolution, right? So you now need to upscale your logs to meet with the resolution of your seismic, so that you can compare, you can match one to another, right? So that's when you now, after doing that, you're able to now populate that. And then data analysis is basically using variogram. Is something you do in Petrol. Everything we are doing here, you're doing in Petrol. So you're using variogram to really understand the distribution of the data across the field, across the reservoir of interest. Then we went again to do model our Pashis and model our petrophysical parameters. And this will go for, as we go further, you see those models as produced. This one will be your Fashi model. If you look at this, if you look at the legend here, you see that your Fashi model is good. If you remember when we discussed net to gross, initial net to gross parameters before, you saw that we had more than 80% sand. So what it means, and if you look at this, the yellow part represents your sand. And if you look at it across board as compared to the darker part, you see that it's actually around that 80%. So it's telling you that we are consistent with the interpretation we are doing. And then again, if you go to see porosity, if you remember also when we discussed porosity, we said it's about 25 to 30%. And if you look at, if you use it to compare what the color distributions and look at your legend, you see that it's still consistent. So that's the same across everything here: volume of shell, permeability, and water saturation. So having built the static model, we went further again to compute the volume. If you look here, you see that we're only talking about reservoir 2 now. Remember, initially we discussed that reservoir 1 and 3 have gas cap. And because of business reasons and because of time constraints, we didn't want to go into modeling or characterizing the reservoir or developing the reservoir 1 and 3, simply because for you to develop all that is a gas reservoir, and basically, you need to, I think the Zoom might be logging us out. I think it's 40 minutes deadline or something. But I think we'll still have up to 10 minutes. If you log us out, please come back to that using that link. We'll still be online, right? So the reservoir one and three basically are gas reservoirs. And for you to actually develop a gas reservoir, you need to have contracts and all that because it's very difficult to store gas. So you want to have the customer, even a contract or a customer before you begin to develop that. So after that, the reservoir engineer was now time to do his thing, and the whole team gathered around her and were able to do a wonderful work in terms of dynamic modeling. So basically a QC of the static model that was already produced initially, and then a fluid model was done, a rock physics model also was done, and then the models were now initialized, and then development strategy presented and results came up. So basically, the data required for this would be your PVC, special core analysis, production data, well completion data, and all that. So going further, this basically will be things that you begin to look at in terms of modeling your field. You look at oil formation volume factor, you look at oil viscosity, a lot of data, a lot of things you already know now go into trying to visualize all these things. And then going further, you want to look at the relative permeability curve. How would this my reservoir perform? If you look at this is relative permeability for relative permeability and this water saturation, and this relative permeability and this gas saturation. If you look at the distribution of the map of the graphs, you understand the trends and what reservoir engineer had in mind to be able to go further to do what she did. And then eventually she was able to get a dynamic volume. When a dynamic volume was calculated after simulation, we saw the percentage difference 0.016. So it kind of gave us kind of some level of assurance that our interpretation has been consistent across. So imagine when you have up to 80, 60% difference, it's huge. But here we have less than 0.5% difference. So I think it was a thumbs up for the team. And so we also went further to now look at the scenarios. If you produce from the 4 wells you already have in the next 20 years, what is it going to look like? Again, if you drill more wells, more vertical wells, what is it going to look like in 20 years? And if you also simulate with horizontal wells, what is it going to look like in 20 years? So furthermore, we went further now to look at the performance across board with horizontal wells, vertical wells, and the existing vertical wells. So if you look at recovery factor, you see that the horizontal well really was so high, 0.62, compared to what you already have from the existing wells, which is 0.17. And if you also look at it, so we're already looking at it in terms of that common that the horizontal well should be prescribed. But this is not just the work you need to do. You're not just going to consider, you're also going to consider your CapEx and OpEx, and then look at the cash flow. So this is basically a trying to just look at what is present oil at the point the oil price was this, and then the general revenue from the field will be this. If you compare both for vertical well and horizontal well, you see the differences, and that's how eventually you begin to look at in terms of if in terms of having analyzed all this, you'll be able to now take a decision. We're able to take a decision that horizontal wells, 5 horizontal wells should be drilled in that field for the next 20 years. So challenges, we have data paucity, non-availability of data. Even the ones we had, there were a lot of poor quality data in it. And then time was a challenge. A project that was supposed to be done for close to 8 months, we had only 4 months. So it made us work through nights, make us work through weekends and all that. So recommendation, conclusion and recommendation generally, we generated a static and dynamic model of the three reservoirs and then in place hydrocarbon was estimated, and then we initialized the model production forecast and economic analysis. It is suggested that 5 horizontal wells should be drilled for reservoir 2 to optimally produce hydrocarbon for a period of 20 years. Thank you guys for listening. Time for questions, and remember, if Zoom logs us out, please log in back. We'll get in again. Can you guys hear me?
Yes, sir. Hello, sir.
Yeah, I'm here.
Okay, sir. Thank you very much for your presentation. I really appreciate your presentation. I have a question on the part of the challenges that you mentioned.
Okay.
I think the first one was a data paucity.
Okay.
So I don't know what really that one means in terms of challenge. What does that mean?
Paucity is just scarcity. It's another word for scarcity.
Okay.
Right?
It's an
So,
English. Okay.
yeah.
Okay.
So if I should have this information, I don't have it. It kind of generates some kind of challenges and all that. But definitely, like I said before I started, there is no project you're doing and you have all the data you want.
Okay.
It's always a challenge in the industry.
Okay. Thank you very much, sir.
So,
hello.
yep.
Yeah, Kaycee, thank you very much for your time, and at least it was indeed insightful. But my challenge, can you hear me?
Yes, I can hear you very well.
Yeah, I saw the structure of the work. It's well arranged and clear, like for someone that has been into that before. But my challenge is actually how to do all of this and its interpretations. Like if you should give me this work now as a petroleum geoscientist to maybe any slide now, I should just interpret this. I think I will have some kind of challenge in doing that. I think that is my own concern. No.
Yeah, just to help you, none of this we've done is rocket science. It's from your basic understanding, from those things you are learning in school. All right? But the thing here is that you're now going to be using your domain knowledge to make decisions. And remember when we started, we only had this a seismic data, hard well logs, right? It was just those things that with
Okay.
software, because we understand, if you talk about picking up a fault, we'll know why we should pick up a fault. You know what a fault does in petroleum accumulation, right?
Yes.
So once you understand those trapping mechanisms and all that, which is your basic domain knowledge in petroleum geosciences, you can go, you now be able to do that. And again, a lot of other things, when you have your logs, for instance, you're trying to do petrophysics, you have your logs, you have your gamma ray. You first, gamma ray have told you that this is sand, which is your reservoir, right? And then you go further to see resistivity. That place that you have sand, is it resistive or non-resistive? Sorry. If you understand that water is conductive and the inverse of conductivity is resistivity. So if water has high conductivity, it's supposed to have low resistivity, right? So it means that our hydrocarbon will have high resistivity. So with that, I can now determine which part of my reservoir has oil or which part of my reservoir has water, right? And because I have now known what neutron and density cross plot does, neutron log basically is measuring the hydrogen index, right? And hydrogen index of water should be more than hydrogen index of hydrocarbon. Hydrogen index of oil should be more than hydrogen index of gas, right? And again, you also look at density. Density of water should be higher than that of oil. Density of oil should be higher than that of gas. So with all these things, I'm able to look at something and say, this is it. Remember, there are a lot of uncertainties because you have high resistivity doesn't mean you're really dealing with hydrocarbon, right? Because sometimes you have a tie sand that looks that a tie sand that is highly resistive, and you begin to think it's highly, but that's, by the way, these are the uncertainties you encounter doing your. I don't know if what I've said is have addressed your concern, Felicia.
Yeah.
Okay. Any other question, any other concern? Okay, then it's time to go. Thank you guys for making our time to join us. Thank you, Stella, the brain behind what we do. And believe me, you is going to even get better.
Thank you very much, sir.
We're going to, from going forward, structure better things and see how we can mutually learn. Everybody learns, and we are fine. Right? Thank you guys for joining.
Thank you very much,
Sir.
Mr. Kaycee.
Thank you very much, Mr.Kaycee. I really appreciate,
Even
because
though
you're giving
even
us a
Mr.
better
Kaycee.
insight on it.
you've